Devadrita, please take the attendance.
Yes, sir. Yes.
Ritam Talukdar has written an answer in the chat box. Please take a look. This looks correct to me. If you have any question, you can ask. Otherwise, you proceed to part B, Q1B, question 1B. Naman Goel and Ishan Daga, both of them have submitted a counter example in the chat box. Please have a look. Both of them looks correct to me. If you have any doubt, please ask. Otherwise, you move to C, Q1C. Rita, I do not understand. So you select 3, that's fine, and no job overlaps with 3. So on the rest of the jobs, I again apply the same algorithm. Hello.
Okay,
Actually,
so
in your instance, every optimal solution will include 3 because 3 does not overlap with anyone.
hmm, yes. So after that we can select one and two means we can come before it. Actually, it will change.
Okay. So are you still claiming that there is a contradiction?
Mm, so maybe not then. Then sir, I have to think
Yes,
something
yes.
more. I
Because there is not any optimal solution will select 3. The algorithm is that you select the job which overlaps with the minimum number of other jobs Once you select that, you have to delete. You can't select the jobs which overlaps with that job. You delete them, and again you apply the same method.
So in the third C part, it is mentioned that discard the jobs that overlap with X. So are we choosing X,
X,
each
correct,
one of
correct.
the
Yes,
overlapping X and discarding the other, or
exactly, exactly. So whenever you say choose X, it's like, so in all three parts, 1, 2, 3, 4, or other parts, A, B, C, D, all parts. When I say that, you select X, right? Select, yeah, choose the job X. And records at the end you see that, and records. That means apply the same method on the remaining jobs. Pick a job X which overlaps with the least number of jobs as a part of your solution. Discard the jobs which overlap with X, because you have picked X, you cannot pick any job which overlaps with X. And for the remaining jobs which do not overlap with X, you apply the same method. Is the algorithm clear to everyone? If it is not clear, unmute and just tell me.
so are we selecting like suppose three jobs overlap with each other, and that's the minimum of the overlap. Are we selecting X at random, or
No,
are we
any,
selecting each X
any,
for one iteration?
any. So for example, in that, in the example what Ritam has written, which is not correct, which is not a correct counter example. So that algorithm will first pick. So for each job, it will count how many other jobs it is overlapping with. And if there are, and it will pick a job which overlaps with minimum number of other jobs. For example, the third job overlaps with 0 other jobs. The second job overlaps with 1 other job, and so on and so forth. Pick a job which overlaps with the minimum number of other jobs, make it part of a solution, delete the jobs which overlaps with it, and apply the same method on the remaining jobs. Is the algorithm clear? In the example, for example, the job 4 overlaps with 2 other jobs. So in the first iteration, I will pick job 3, make it part of the solution. No other job overlaps with 3, nothing to delete. Then in the next iteration, I will pick what? I will pick maybe 2, second job, because it overlaps with only one other job, and so on. This way I'll go.
So that's what I'm asking. The selection of two, the first time we select three, and then for the second selection, do we select 2 or 4, or do we select
Anyone,
at random?
anyone.
So, but that matters, right? If we are selecting any one job
Algorithm
at random.
says algorithm says not random. Anyone is, if you pick anyone, that is fine. For example, in the greedy algorithms that we have discussed in the class, both Huffman coding and machine scheduling, there also the minimum or whatever is thing is may not be unique.
Okay,
That
sir.
case you do not come to you can do random, but it doesn't matter. Pick anyone, and both the things will lead you to optimal solutions. Optimal solutions may not be unique. That's it.
Okay, sir.
So Ritam, are you saying anything? Your voice is very low.
Sir, is it audible? Hello.
It's not very audible.
No. Sir, I'm joining again.
Yes, now I can hear you, Ritam. Yeah, last time I am joining again. I can hear. Oh, sorry, I think he pressed.
Hello, sir. Am I audible now?
Yes, you are audible.
So, sir, like in the example that I gave, so suppose if the algorithm takes any and guarantees the optimal solution, then sir, it might take 3 and 4, because both 3.
No, it don't take 4, because Just after, okay, in the first iteration it picks 3.
Okay, sir, got it. With 4. Okay, that's why it won't take.
Yes, correct.
Okay, sir. Then I
Okay.
guess it might be optic. Okay.
How many of you think that this is a optimal algorithm? Just raise your hand. None of you think, okay. Ishan thinks, okay. Very few things. Okay. How many of you think otherwise? Others, yeah. How many of you think that it is not an optimal solution? Just raise your hand. Okay. Yeah, let me give you a little bit of hint. So prove that it is not an optimal solution. So look for counterexample.
Sir,
Yes, tell me.
like if there's a job which is overlapping with one and I have written all those jobs and there's some time remaining and there's another job which has two overlaps, will it go to the job or else will it discard?
I'm not getting. So if it overlaps, then only it will discard because job can't be done partially.
Ah, yes, sir. Okay, sir. Okay, understood.
Okay, so let's try to find a counterexample together. How about that? Or do you want to try more? My screen is visible, right?
Yes, sir.
So this you will see, I said that there are some algorithms for which it is really hard to find a counterexample, and this is one of them. So closely observe the process of constructing the counterexample. The way I have understood this is as follows. So in some sense, we will force the algorithm to make a wrong decision in the first step itself. So this is one job, and and we want this job should not be picked in an optimal solution. That's sort of I want, and but I will force the algorithm to pick this job in the first iteration itself. And once it picks this job, it can never reach the optimal solution. That is the idea. So, so where is the optimal solution? Maybe optimal solution. Suppose this is the optimal solution. So yes, this satisfies the condition that yes, if it picks the top job, then it can never reach the optimal solution. Agreed or not? If you do not agree or have any question, you just unmute and speak. So it satisfies the first condition. If the algorithm picks the top job, it cannot go to the optimal solution. But the algorithm does not pick the first job. Will not pick the first job because the algorithm uh, picks the job with smallest number of overlaps. Agreed? And that in the current stage, the first job overlaps with two jobs, and the bottom two jobs each overlap with one job. So in some way, I want to I want to make the number of overlaps of the top job least, so that the algorithm picks the top job in the first iteration. Again, I want to force the algorithm to pick the top job in the first iteration, and the only way I can do this is to add some more jobs so that among all jobs, the minimum number of overlaps, the top job has the minimum number of overlaps. So, okay, so the top job has two overlaps. So let's make the other bottom two jobs three overlaps. Add two more jobs. Okay, now I am able to make the algorithm force. I'm able to force the algorithm to pick the top job at the first iteration. But now it is not the case that that okay. Let me use some color. Red job. Red is danger. And let me use green color. This was where we started, and we want these green jobs to be part of optimal solution. Now, after adding these four white jobs at the bottom, now green jobs are not the optimal solutions. Actually, there is an optimal solution picking the red job. You pick the red job and one job from left and one job from right. Green jobs are not at all optimal solutions. Two green jobs, or if you pick a green job, then you are not leading towards optimal solution. No optimal solution in the current instance contain any green job. That's not what I want. I want I want an optimal solution which includes these green jobs. So to do that, the trick that I do is this: I add 2 more green jobs. What is the situation now? If I pick a red job, then among this left yellow part and right group of jobs, this left yellow box and right yellow box. If I pick a red job, the immediate 2 green jobs which are overlapping with red jobs, they are gone. I can't pick them. But also all the 3 boxes in the boxes, they are mutually overlapping. You can pick only one of them. So if I pick a red job, then I can only pick 3 jobs in total, red job and 1 job each from the yellow boxes. On the other hand, if I pick a green job, I can clearly see that I can pick 4 green jobs. So here is a counterexample where the algorithm will fail, because let's verify that indeed the red job is the one which overlaps with the minimum number of jobs. So let's write each job how many other jobs it is overlapping. Red job overlaps with 2 other jobs. This job overlaps with 3 other jobs. This is 3. These are 3, 3, 3, 3. No, this is not 3. 3, 3, 2, 2. Although this is a valid counterexample, but you see, there is a tie also. I do not like tie or anything. I want to force the algorithm in the first step itself to do the mistake. There is no tie. I want to remove the tie. Can someone suggest how I can make the red job the minimum the job with the minimum number of overlaps? Currently it is one of the jobs which have minimum number of overlaps. I don't want one of them. I want the job. The red job should be the job which overlaps with the minimum number of jobs. So that there is no confusion, no nothing, and the algorithm is doomed to fail. Please suggest how I can make with little bit of change to this instance the unique job. Red, yes, tell me.
So can we make another job which goes from the green job with 3 overlaps to the green job with 2 overlaps? So
Yes, I think what you are saying is right, and that is the idea. You can add this sort of jobs. One more. What's the harm? These white jobs. One more job. So if it is one more, then now you see that this numbers changes slightly. All these numbers are increased by 1, but red remains same. So this becomes 4, 4, 3, 4, 4, 4, 4, 4, 4, 3. Can you see that now even tie breaking will also won't save that algorithm? There is no tie also. This is a counterexample. Any question on this counterexample? Has everyone understood? If you have not understood, if you have any question regarding this counterexample, then please ask. But what is important is not this counterexample. As I was stressing in my earlier lectures also, the importance is the process. In your future life, you apply greedy algorithm and you need to imitate this process. So the process of constructing a counterexample. Okay. Okay, so if you don't have any questions, so you go to the next question, question 1D. Let me stop sharing. Yes, tell me.
So are there ways in so if if this were the right proof, what would be the steps by which we could prove it using the exchange argument?
Sorry, I do not get. Again, ask your question.
So initially I thought this was an optimal solution. So I was trying to apply the exchange argument proof on it. But so I reached a point, but after that it became hard to prove. So should I send my solution in the chat?
No,
Okay.
but I am glad that you are not able to prove, because there is no proof. All proofs that proves that this argument, this algorithm is correct is wrong. All proofs will be fallacious. And if you are sincerely doing your proof, then you should get stuck.
Yes, sir. But my question was that so this is different from the Hoffman coding
Hoffman coding.
one, not Hoffman coding, the initial problem which we solved using
Correct.
exchange argument. In the sense that over here, after choosing a particular job, we have two completely different subsets of jobs left from which we can choose the next job. So I could not explain how the exchange argument can be used.
You could not apply exchange argument. If you are able to apply, if you are succeeded to apply exchange argument successfully, then you would have proved. The very fact that you are not able to apply indicates that because as I said here in this case, I told you that it is not a correct answer, correct algorithm. So, but for other cases, when you don't know, you should try both the approaches in a time sharing manner. At the beginning, you believe, okay, this looks a correct approach. Let me try to prove it sincerely. Don't lie there. And if you are sincerely trying to prove it, you will get stuck. Now, once you get stuck somewhere, then you suspect, okay, maybe there are two reasons that I'm got stuck. Either I'm not able to prove, and the second reason is that the theorem that I'm trying to prove is not correct. Then you sort of suspect, okay, maybe it is not correct. Then let me try that other path also. Let me try to prove that this is not correct. Anything in any unresolved theorem whose proof is not available, it's not like theorem, because in some sense we do not know whether it is correct or not. We believe it is correct, whether P equal to NP or P not equal to NP. We believe P not equal to NP, but that's only belief. It's not a proof. So that's why you should try in a time sharing manner both the cases.
Yes, sir.
Okay, but in question, yeah. Now let's go to question D. And I would strongly encourage you to practice this process. This process, this is not like learning one algorithm or two algorithm or 10 greedy algorithms. It should not be like that. It's like you should practice this process closely, watch this process of algorithm design, greedy algorithm design with many problems. And then the more you practice this process, the more you will be master of this process. It's like recall the rule of 1/4. The 1/4 knowledge that what I can tell you, I have told you. Next, your 1/4 is reading greedy algorithms and practicing it from all the reference books given. And with peer groups, then you discuss your solutions, because in this tutorial itself, there are so many problems we are only able to do because of this limited time, the first three. What about the rest? And teacher will also will not give model solution. Model solutions they may give only for exam questions. Then the peer group study will help. It will help you and everyone. And these things you do for some time, the fourth component of 1/4 rule. Then only you will be a master of greedy algorithm. Okay, I'm almost out of time. You can start doing question number 1D. Yes, so T is clearly not the right algorithm, not a correct algorithm, and Ritam has shown a counter example. Then go to E, 1E. I think I'm out of time today. So yes, practice these questions and closely practice this process. Study this with all the reference books and discuss these solutions with your friends. Okay. So that's it. From next week we will start dynamic programming algorithm, and we will have Saturday's tutorial from 6 p.m. Right, PPC? We are meeting again at yes.
Yes. Saturday 6 p.m.
Saturday 6 p.m. Yes. Okay then. So if you have any question, you can ask me. Otherwise, you can leave. Okay. Okay. Thank you. Thank you very much. Practice. Bye bye.